Click record. Okay, so let's continue our troubleshooting. Let's get into power distribution. So you got a window. This is why understanding transformers is important. Because not that you need to know. I mean, it's good that you know all of the different voltages that you can run into. Uh, but more so, and this is what I was trying to explain last week. I hope it came across. When it comes to the transformers and all the voltages that I was talking about with delta, the delta high leg, corner, grounded. First of all, high leg delta and corner grounded delta, it'll probably be very rare. High leg you may run into, corner grounded unlikely. These days they're just phasing out of the world of electrical. So more likely you guys will be running into Y fed systems. All right, Y fed systems. Now, are you going to be opening up power distribution transformers? No, just a measure. No, you're going to be in here. You're going to be in panels. So there is where I was trying to communicate that last week. Understanding the voltages, what delta has, what Y has, or how to, which one's 480, how to understand 208 versus 120, is because you're going to be in a panel. Panel's going to look like this. All right, now the panel is giving me some information right now on the voltage. All right, one of the things that those who went through the code classes will get some information on, which I'll point out. All right, there's some articles in the code book, and I'll give you one article in the code book. This is going to show up in a few places throughout the code book, but one of them, and I'll drop back over to article 210. So feel free if you have your code book nearby, or you can just write this down for right now. I'm just going to walk you over to the article. Again, those who did the code classes will recognize some of this. And for those who haven't, you can write down article 210.5, or again, if you have your code book nearby, you can grab it. And what this is going to get into is color coordination between the conductors. All right, again, it shows up in a few articles, article 310, article 220, and this one in article 210, identification for the branch circuits. All right, meaning that there's a way to color coordinate the conductors to let everyone know what the wires are versus neutral versus hot versus grounding conductor. All right, now the articles themselves that give us the color for a grounded conductor, the neutral, or the grounding conductor, the ground, are here. 250.19 for the ground, 200.6 for the grounded. What this is going to tell you is, and you might know these already, all right, which is, and you can see it here, all right, which is, let me use another color since it's a little bit dark. All right, these are our neutrals. The neutrals are either white or gray, and grounds are green. They could also be bare copper. Now, you don't have to write any of this down because this class isn't about this. This is a code thing. You can come back to the code and check some of these out. I am going to point to the thing that I am going to talk about in relationship to power distribution. So, like I said, white or gray is for the neutrals. White is for the low voltage systems. All right, this is for the low voltage systems. And gray is for the higher voltage systems like 480 and 277. Ground is green for everybody. Doesn't matter what it is. And here you can see 3 coordinated colors of black, red, and blue for the hot conductors. All right, I'll move it down here. Black, I guess an L would work here. Red, and then blue. All right. So this panel is giving me some indication as to what voltage is here. It's telling me it's low voltage because 1, I have the neutral, and 2, the black, red, blue represents the lower voltage as well of the voltages, right, or the lower voltage system. So black, red, blue would be for 120, 208. In fact, I think I have this written down somewhere. I don't want to search too long for it, but I could help for anyone who, hey, I'd like these as to grab them. Let me see if I have them. Yeah, I don't have them here. I'd have to take a minute to find my notes as to. Oh, there it is. Found it. All right, here we go. Just to help. 210.5, right? Because I also teach this course along the way. So just to help, you can write this down, take a picture of it, whichever one. If you know this, great. So when I see a panel, here I'll show you a panel, 2 panels side by side. The one on the left is telling me low voltage system, 12208. It's 100% a Y transformer. Again, these days, it's all you're going to run into. The one on the left is telling me brown, orange, yellow. You'll notice the gray neutral sitting right there. Now, the reason for all of this, again, we get back to power distribution. And you get back to troubleshooting. When it comes to troubleshooting, you need to know and how to identify which circuits are going to be coming from a high voltage system, or I should say, not which circuits are coming from which circuits are likely coming from a high voltage system. Are they 100%? I don't know. We can find it, maybe they're not, but we need some direction to try to go look for things.
So the one on the right is what?
This is 480, 277.
On Y system too?
And Y as well. Yep, they're both Y. And again, we know we know it because of the neutral, because the ungrounded delta would not have a neutral. And then the high leg and corner grounded are low voltage systems. They're not the 480, 270 or 480, 240. The only 480 delta is 480, 240. Oops, excuse me. And it doesn't have a neutral. So knowing that about the delta, that it doesn't have a neutral, when I open up a panel and I see a neutral, that's how I knew to identify this as a Y transformer. That's why I knew. Now, do you absolutely need to know that part of it? Not really. I mean, to answer questions here in class, of course, but to, do you need to know the Y, the transformer's Y or delta? Not really. Not really, but it is good to know that you have a neutral in this panel. So it is good to know that's a Y, because if I need to run now I wouldn't run an outlet. I wouldn't set up like a standard electrical outlet because I can't set that up at 277. I mean, I can for some machinery, but I can set up a lighting circuit. All right, I can put some lights here because I got a neutral. I got a neutral that I can send to this light. So this panel here would be a very good panel for commercial or industrial building lighting systems. Now, the one on the right, I could also identify as a Y transformer, even though if you open up a high leg delta transformer, a high leg panel, it is going to have black, red, blue. All right. Actually, it might not have red here. Usually they try to identify the high leg, which, by the way, was an exam question. The high leg's on the B phase. With another color, usually orange. Some states use orange. New York used purple. It doesn't, the code doesn't really tell you what you have to color it as or define it as far as the color goes, but some kind of. And once it is, then it's that for the whole building. So once we establish that we're going to use purple for the high leg, then that becomes the high leg for the whole building. So one, that's how I know this isn't a high leg. But two, the corner grounded delta would also be like this, black, red, blue. That one would not have a different identified C phase. Excuse me. But the reason I know this is not a high leg, excuse me again, is because, and you might not be able to see this too well on the screen. Maybe you can, maybe you can't. These are single phase breakers. And all of the phases are taken with single phase breakers. And remember what I mentioned about the high leg panel. The high leg panel will not be able to create a single phase off of the B phase. That's the high leg. That's the one that would be wrong. You can't send this over to an outlet because the outlet would have 208, and whatever you plug into this outlet would either fry up if it's a computer or not work because the voltage is too high going in. This is the big benefit of Y panels or Y systems, is you don't have to worry about that. All of these could be single phase outlets. This could be for the school that you're sitting in right now, with all of my single phase circuits for a bunch of outlets throughout all the classrooms and hallways and etc. Now, do you have to memorize all that right now? No, that's a lot that I just threw at you guys. So, but now you have a window into. We use different systems or different color coordinations to identify different systems. All right, and going back over here, this is all you really, you don't have to worry about the neutral so much, although remembering gray and white is not too difficult for either one. But the brown, orange, yellow, by the way, this is boy, easy way to remember it. And then the other part is, not only do I know what the voltages are, by the color of the individual conductor, I know whether it's A phase or B phase or C phase. Meaning if I see a yellow wire somewhere in a junction box, I know it's coming from the C phase. If I see a blue wire somewhere, I know it's coming from the C phase. A red, an orange, and for the most part, again, 99% sure, could somebody have used the wrong size color wire because they didn't have, one in the truck when they showed up to do some extra work? Yeah. That's okay. In a pinch, it's all good. Try not to do that as much as possible, but so that's again what this panel is allowing me to understand about it. If I see one of these red wires somewhere in a junction box somewhere, I know it's coming from a B phase. All right, so if I need to make sure that I have two different phases, there's where the colors come in to help me out. If I need 240, I can't have two B phases. You can't pick up a red and pick up another red. This is not going to equal 240. Yes, it's 120, and that one's 120, but when you measure between both of them, you're going to get 0 because you're measuring between the same phase. For you to be able to get 240, you need a different phase than the one you're looking at. If you have A phase, you need a B or a C to get 240 off of it or to get the phase-to-phase voltage. So here's where the colors come in. Now here's where the code gets involved. The code mandates this. All right, I'm going to pull away from this. We're going to go back over to power distribution. So when it comes to power distribution in a building, where was I? I think I was here. Nope, I was here. Yes, all right, coming back. I'll show you the code. This is why I went over to this one, because when you're an electrician, an industrial electrician in a building, right? One of the things that you are almost 100%, if not 100% of the time, have is two different systems in the building. Like what I was just showing you. You'll have the low voltage panels doing their job of feeding outlets and general low voltage electrical systems that need 120 and stuff like that. And then you'll have the bigger 480, 277 taking care of the lighting system, taking care of the larger equipment that needs the higher voltage to run. So because we are very likely in commercial and industrial buildings going to have two different voltage systems. That's what they're called, two different voltage systems. One low voltage, again, one high voltage. Then you have to distinguish them, all right? And Article 210.5 1, actually it's C1, that's how you would say that. All right, so it would be 210.5C1 gives us that. It says branch circuit supplied from more than one nominal voltage system. Where the premise wiring system has branch circuits supplied from more than one voltage system. All right, so in other words, it's saying where the wires in the buildings are supplied from two different voltages, like the low and the high. Each ungrounded conductor, here's where it tells us, each ungrounded conductor shall be identified by the phase, black defining A phase, red defining B phase, blue defining C, and then brown, orange, yellow doing the same, and the voltage. The black, red, blue defining 120, 208, brown, orange, yellow defining high voltage, or 480, 277. Now, it doesn't say that you have to use black, red, blue, brown, orange, yellow. It just says that you have to use two. It doesn't even say you have to use two different colorings. It says you have to be able to identify all of the different phases and the voltage system. So you're going to end up having to use different colors to represent them. So in the US, we picked these. I don't know who did and when they did, but they picked them. This is not a code mandated anything. Black, red, blue does not have to be 120, 208. Brown, orange, yellows does not have to be 480, 277. But at this point, trying to change that in a building is going to get that failed by an inspector, because the inspector is going to say the standard now and these days is brown, orange, yellow for 480, 277 with the gray neutral. Actually, the gray and the white, that's actually, you're supposed to use that, but. All right, so this is the code that tells us we have to use those separate colors for the high voltage and for the low voltage. All right, if there was any follow-ups there. So for power distribution, I just want to identify them. All right, I want you to understand the different types of power distribution systems that we have. All right, so you're in the building. You're going to have three types of panels, right? Three types of electrical panels. So the first one is a short, abbreviated to MDP. This means main distribution, right? First, the word up there, distribution panel. All right, a main distribution panel. Sometimes it's called an MSP, main service panel, but I've always used the term distribution. I've always seen it on blueprints as MDP. So your main distribution panel, this is the one that's going to receive the electricity from the electrical company, connected to utility. Oh, there we go. Too many. All right, there we go. Connected to utility. You have nothing to ever really come over to this panel to do. All right, in an industrial commercial building, your main distribution panel is the one that's connected to the utility company. It's getting the big voltage coming in, the large conductors coming in, and this is going to have main breakers in it. All right, I'll put it down below. All right, we'll have main breakers for there we go, sub panels. All right, this will have the main breakers for the sub panels.
What does that mean?
I'll define sub panels after.
Well, I know it's like.
Oh. So then, what do you mean by what does it mean?
Oh, okay. So I can just grab one of those, yeah, right, and make a sub.
Right. Okay. Yeah. Let's put a visual to this. Let me see if I can find one. Let's go. Let's look for a main distribution panel. Maybe I can just put MDP panel. I can find a large one. Okay. Yes. So this is what they're going to look like. They'll be gigantic, something even that large. All right. Not that big. Here's a. Let me see if I can go to a little bit closer up of that one. This one's on eBay for some reason. You go buy this one. And let me see if I can get close to that. There we go. Should be able to see that. If you look at this one, you have these large breakers in here. These main large breakers with a large breaker on the bottom. This is your main breaker to the whole building. If you shut this off, the whole building goes out. And then these breakers in there, these large breakers, are feeding sub-panels like the one right next to it. And then this panel is going to be the one that has all of the smaller breakers in it. Not the best image. Let me see if I can find another main distribution panel. Well, nope, that's the... Yeah, there we go. There's a better close-up of it. You can see these large breakers in it. Now, the...
Those aren't at homes, right?
No. This is not a home. This is commercial or industrial buildings. In a home, it's different, and I'll go over a home as we get to the end of this. All right, but a home is different because a home is going to have the panel is connected to the utility company and connected to all of your little breakers that you're going to go and turn off and on and stuff like that. Different from a commercial building where a main distribution panel, there's no troubleshooting here. All right, which is what I was going to put. No troubleshooting here. Unlikely that you'll ever have to touch this panel. All right, this panel is again, maybe a 2,000, 3,000 amp panel. Stay away from that thing as much as possible. Don't even open it up. Very dangerous to get inside of it. In there, you're going to have, like I said, these large breakers that are feeding your other panels. So that's all that's going on in here. The utility company is bringing power to this panel, and this panel is sending power over to other panels. So to ever need to come over here and troubleshoot, it means that you've had a problem with the power that's feeding the other panels, and it's just unlikely that you'll have to run into anything like that. All right? Usually, our troubleshooting is done not on the main big stuff, but on the smaller breakers that are feeding the branches, the branch circuits. All right? You don't have to memorize the term branch circuit, but the branch circuits are the breakers, the circuits that are leaving all of these breakers and going to things like outlets and lights and, you know, motors and our loads. All right, the loads, the motors, the lights, and the outlets. So nothing inside of a main distribution panel that you need to worry about. But obviously, you need to know that this is your main panel coming, because if somebody comes into your building and you're the maintenance person and they're like, hey, where's our main distribution panel? Or we have a utility company is going to come do some service, or you need to walk somebody over to your main distribution panel, you should be able to identify it. All right, again, it's connected to the utility company, and it has our large main breakers for the sub panels, which is the ones we'll talk about next. Sub panels. These are where we do all of our work. All right, these are connected to the main distribution panel, to MDPs. By the way, some buildings I've seen that have had 2 main distribution panels. If the amperage of the building, the load demand of the building is a lot, then one panel becomes too small and you need 2 of them. This happens as well. But then you would have 2 MDPs and still no troubleshooting, and now 2 of them. So there was 1 and now there's 2, but you still don't touch either one. Subpanels, these are the ones that we're going to be focusing more on. These are the ones that are coming off of our, and these will have our lighting panels. All right, this will have lighting. This will have general, receptacles, if you want to write outlets. This will have our motor loads, motors, and equipment connected to your sub panels. All right, so if ever you need to figure out an outlet isn't working, we don't come over to the main distribution panel. You will find the sub panel that has your outlets connected to it. Now, which one is it, Mr. Okay, which one is it? Well, it's not the one with brown, orange, and yellow, because that's high voltage. So if you're standing in front of 4 of them, and 2 of them are 480, 277, you can eliminate those 2 as the ones that are feeding your outlets, and now you're down to 2 panels. Now, you're still only down to 2 panels, so I didn't find the outlet, but it's not the other 2. It's not the main distribution panel in here. I walked into the electrical room, there were 7 panels, and I've narrowed it down to 2. All right, now, tomorrow we're going to talk about tools that we can use to troubleshoot outlets into those panels, but that's what I'm trying to help with today, understanding where do I go when I'm trying to specifically, I'm looking at an outlet, or I'm looking at a light, or I'm looking at a motor. And this is where that's why I started with the color coordination, because it helps a little bit. Now, if I'm looking for, again, general receptacles, I'm looking for a panel that looks like this one. Brown, black, red, blue, with the white neutral panel. Sometimes on the outside of the panel we'll get the voltage information, but most of the times you're going to have to open the panel and check it out. It's only 4 screws on the outside. Pop it open. Uh-oh, wrong one. Put it back. Sometimes as you become more experienced, just by looking at the breaker itself, I'll be able to tell you this is a low voltage panel. But I don't want to teach that right now because that's getting a little bit too deep into that. You'll learn that one. That one will be a hard one because I also have to like go through different manufacturer of breakers, but when you see enough, you'll be able to just look at a breaker at some point and go low voltage panel, high voltage panel. But right now you can't do that, so at least you can do it through the colors of the conductors. And again, I'm looking for lighting. Lighting's a little bit tricky because lighting can be off of a low voltage panel. It could also be off of a high voltage panel. They're better to look at the light itself, right? If you're troubleshooting a light, you will have already identified what conductors are being used for this light fixture. If you see brown, orange, or yellow, you understand this light fixture is 277 connected now. And now when I'm going back to a sub panel to look for this lighting circuit that's not working, I'm looking for one of the higher voltage brown, orange, yellow ones. All right, motors and equipments, 480, 277, high voltage, almost 99% of the time. So again, just knowing a little bit of that color coordination helps you identify which panel a circuit could be coming out of that you need to troubleshoot. Again, not trying to make you experts just yet, but trying to give you a direction. Direction is right now all we're needing. All right, we'll talk a little bit more about one other step in power distribution. Although I need to wait a little bit to get there. They'll look like these guys, the disconnects, but let's wait to get there. Those will be one last step. But if anybody can think of a question on this for now. Now, how many sub-panels? That I can't tell you. That's size of the building versus. Little building, maybe one main distribution panel with, at the very least, these are the sub-panels you're going to have. You're going to have a lighting. You're going to have a general receptacle panel, usually different from the lighting because of the high voltage lightings like to use and the low voltage that general uses. Your motors will have their own panel. If you have a bunch of motors, maybe that's 2 or 3 or 4 panels. You know, if you're looking at a water treatment plant with a lot of water pumps, then we got a lot of motors. If you're at a UPS warehouse with a lot of conveyors, with a lot of motors for all of that moving of the boxes, you're going to have a lot of motor panels. Equipment, same thing. These are at the very... And then there's a couple of ones that are not part of something that we troubleshoot, but they get their own panel. Sometimes, not always. Like the elevators. We don't troubleshoot elevators. That's the elevator companies. You got to be licensed for that. They have their own journeyman. Fire alarm panels will also be a panel, but fire alarm people get in there. You know, this now gets into legal things that you're allowed to touch and not touch. But generally, these are the ones you can... Fire alarm panels, elevators, and specialty equipment, maybe not. Okay, so from here, let's now identify the breakers, right? So these are the panels, and now there's a couple of style panels. Let me actually fall back and show a little bit of that. Yeah, where do I have it? Here we go. I just want to show a different panel, not a 3-phase. All right, this is a single-phase panel. And you'll notice we only have A phase here and B phase here. This one is not residential. I can just tell by the way it looks. This is a commercial building. It is single-phase commercial buildings. They could have that. You know, they don't have to be 3-phase. They just tend to be 3-phase sometimes, but this is a single-phase panel. And so in single-phase panels, you only have A phase and B phase. And you got some colors here. You got a red. You got black conductors. You don't really have blue. Why? Because you don't have C phase. C phase is the one that would be the blue. Right? So there is another thing that I can identify just because there's no blue conductor, meaning I don't have a 3rd phase. All right, so there's a few things that I know. Also, we know that it's low voltage because there's a white neutral There's another thing that is giving me some identification. And then we got a couple of other things that are like the bare copper back here. This indicates low voltage versus high. But don't have to get too far into the copper. Those are just, again, we can identify the low voltage because they're using a white neutral. There's a couple of red conductors in there. They're using black versus brown, orange, and yellow. I think I have another panel here, but that's the one you guys saw. And then we have the ones that I had here. These are the ones that I had. All right. I don't think there's anything else that I'm looking at that I want to point out. So, unless you have any questions, though. Now, different style breakers. So, let's go over to breakers. All right, so we have 3 different type of breakers. I'm going to go one by one for each breaker that we have. This might seem simple if you know about breakers. This will be a little bit simple, but I do want to make sure everybody understands everything about all of these devices because they're important for you guys to know. So this is a single pole, P-O-L-E breaker. Single pole, that's how we say it. All right, now this breaker is going to only have a single connection point. All right, this is going to have a single connection point. And these single pole breakers have a limit. All right, you will only find these in technically 15 amps, although technically not allowed for commercial and industrial. That's only for residential, but it does exist, so we'll write it. 20 amps and 25 amps. All right, they also make 30 and 35 amps, and that's it.
You say those are for just residential, right?
The 15 is only for residential. You're only allowed to use 15 in residential. Commercial buildings and industrial buildings, 20 amp and above. And this has more to do with the wire, the number 12 versus the breaker itself. But so in a residential panel, you'll find 15 amps for a couple of circuits. Even these days, not too much is allowed to be 15 amps. I think you're only allowed to do bedrooms these days. I think hallways are allowed to be 15 amp circuits. It used to be bathrooms, but now bathrooms have been upgraded. They have to be minimum 20 amps for the bathrooms. Kitchens have to be 20 amp circuits. Dining room, since it's connected to the kitchen, has to be 20 amp circuits. So these days, and they're starting to phase it out even more. And there was rumor that they were going to get rid of the 15 amp breaker altogether in general electrical use, but so far, no go there. It's still around, so we'll put it. So that's it. You can't find a 40 amp breaker, a 50, a 60 in single pole. All right, single pole breaker. Now, when you go to test this breaker, all right, this is the part I want you guys to understand also. Excuse me. The breaker is a switch. All right, so power comes in from the side that you connected to the panel. It's always over here that power comes in, and power goes through the breaker and distributes out the back side of the breaker or where your conductor lands. All right, this is where the power goes out through. So how do I remember when I said bad breaker yesterday? We landed at bad breaker. I'll pick up a little bit now that we're here with this one. So bad breaker was also, going back over to where we're at, if you have, remember we solved it when we're trying to understand the overload. So I have to leave whatever is connected to this breaker on. I have to leave the breaker on. I'm going to measure amperage. And if there's a little bit of amperage on that 20 amp breaker and the breaker trips, then I know I got a bad breaker. So that's one of the ways a breaker could be bad, meaning it can't hold the amperage that it's designed for. It's a 20 amp breaker and it's tripping at like 8 amps, 2 amps, 5 amps. This is no good. We want the breaker to trip only when it gets to 20 amps. So that's one way a breaker can go bad. The other way the breaker can go bad is it's not giving you voltage. It's not about the holding of the amperage. It's just that when you've turned it into the on position, there's no voltage back here. It's the other way a breaker can go bad.
When you check for amps on your multimeter, what setting is that?
Okay. So for our multimeter amperage setting, And I'll give you more of these notes tomorrow. That is going to, there we go. Where's my amperage? You're going to set it to amperage, or you're going to set it to, let me go close up to there. And it depends on your meter, right? You might only have one amperage setting.
Yeah, well, mine says 40 amps and the other says 400 amps.
Yeah, so it depends on the circuit that you're going to be measuring. Now, you should have a rough estimate of the amperage that, if you're at a breaker, you should have a rough estimate of the amperage that you're going to be checking, because you see the number on the breaker. So you just want to make sure that you are using the 40 when it's less than 40, and then using the higher one when you're above it. Now, could you turn it to the 400, I think this is what you said, and measure 8 amps? Yes. You can turn it to the 400, and you can measure an 8 amp circuit, or measure 8 amps on a wire. But it's not going to be very accurate. It's going to be off by a little bit. So when you turn it to the other setting, it's just going to give you a more precise number. So, and you actually measure, it might be 7.6, not 8, or 7.2, not 8. And sometimes this is important for us to know, that because you're dealing with small variables sometimes. On a 20 amp breaker, the difference between 16 amps and 19 amps is only 3 amps, but it makes a difference on that breaker. That breaker will trip at 19 amps after a little bit of time, not immediately, but after a couple hours. If you still have that breaker and the whatever you have running on at 19 amps on a 20 amp breaker, that breaker is going to pop. So the difference between sometimes a little bit of amperage, or knowing that there's a little bit of a difference, could be where you want to use the different settings for. All right, so that's one way that the breaker goes bad, because it can't hold the amperage. The other way the breaker can go bad is it's not giving you voltage on the output side.
And to check the amperage, you just put the hot on that side and the black on the ground.
Exactly, very good. Either one, I was going to say, when you check, you can check between hot and ground, or hot and neutral. I'll put it over here. Either one is fine. If you're in a panel, go back over here. Either one is fine. I put my meter, I put it on the point of the, and as my advice, leave the wire on. Don't remove the wire and then try to leave the wire on, because that little screw that's holding the wire, when it's holding the wire, it's tight, and that little tight connection onto the wire is the bond you want. If you open up that screw and remove the wire, that screw is now loose, and sometimes when you're putting your meter on there, you don't get a good connection on it. So leave the wire on. Now, do you have to memorize? You don't have to, if you forget that, it's okay, but other side to the neutral is fine, or other side to the ground is fine. Whichever one is, least dangerous to have with your meter, keeping in mind you're using 2 hands now.
You have it opposite, right? Like the red cable goes to that red cable.
It doesn't matter with AC voltage.
Okay.
With DC voltage, it does, because that's what it's indicating, positive and negative. So for DC, I would put the red on positive and the black on negative. But for AC voltage, it doesn't matter.
Okay.
Good. Yeah, these are all important questions so anytime you're thinking of stuff like that, ask them. They're good. All right, so, oops, there we go. So to check this breaker, it's either hot to ground or hot to neutral. Single pole breaker. All right, now, a 2-pole breaker. All right, this is the other type of breaker that's out there, which is a 2-pole breaker. Now, this one I don't have memorized as far as how many how high it's going to go. This one I did because there's not many. I can, you can remember those numbers. But this one goes well past 200 amps. I don't know if they make a 300, so I don't want to put numbers that. But here's the ones that they don't make. They don't make a 15 2-pole. All right, no 15 2-pole. They do have a 20, they do have a 30, and so on. So the numbers on this one doesn't really matter. This one, yes, because again, there's only a few, but this one, not so much. Now, this one is going to disconnect two hot conductors simultaneously, or at the same time. I'll use the word simultaneous. think I spelled that right. And the code demands this of us. Sometimes on some circuits. Sometimes on some circuits, the code needs us to disconnect both ungrounded conductors at the same time. In fact, right on that article that we were at, 210.5, where I was showing you, right before that one, right over here, when it talks about multi-wire branch circuits, all right, multi-wire branch circuits, which a multi-wire branch circuit's just a bunch of, these are multi-wire branch circuits. Come back one here. These are multi-wire branch circuits. All right, when one hot and another hot share a neutral into a circuit, they're called multi-wire. We don't have to get into the definition of that so much. I just wanted to point out this rule that it says here. Each multi-wire branch circuit shall provide, or be provided, excuse me, with a means that will simultaneously disconnect, go up here, all the ungrounded conductors at the point where the branch circuits originate, which means at the panel. So for these multi-wire branch circuits, if you're using two hot conductors to feed a multi-wire branch circuit, let's design this for example. I have a panel, and I have a, we'll go to a house so it makes it easier. Let's say I have a water heater. My water heater operates off of 240 volts, meaning one hot and another hot. From two different phases, right? We need one from A phase, one from B phase. They can't both be from the same phase. At the panel, these two wires cannot, here's what they cannot do, they cannot land on two separate single pole breakers. All right, you can't put one single pole breaker and another single pole breaker here.
What's that? W in the H?
Water heater.
Water heater, okay.
Yeah. Just trying to anything, but something that was 240. Now, in a pinch, can I do this and, just resolve it for the homeowner maybe and just get them working because I didn't have one of these in hand? Okay. But the reason why I can't use two separate individual single pole breakers is because they shut off independently of each other. So if I shut one off, the other one doesn't shut off along with it. And they're not worried so much about shutting off because if you shut off one, you're standing in front of the other one, you can shut it off too. What they're worried about is a problem on the water heater, like a short circuit, and it trips the breaker, but it only takes one out, and the other one is still on. The other one's still hot. And now you have one hot or one live and the other one off, and this gets dangerous for somebody coming to check it. So in the event of a short circuit on a circuit like this one, we want a two-pole breaker here with, like you can see here, one handle that simultaneously will kick both of these off at the same time. And again, here, go ahead.
Those will never power two different things, right?
Exactly. They will not power two separate things. If we wanted to power two separate things, now we're at two single pole breakers. All right, these will power one thing that requires 240 or two phases on it.
Okay.
All right, they have these for the higher voltage and they have them for the low voltage as well. As far as breakers go, they're on both sides of the voltage world. So, and again, the reason why you cannot is because, sometimes I just like to point out the codes that tell us we have to. Right, this is the one that says we have to set it up this way. So, why do I need to know that? Because if you're working in a building as the industrial electrician, you are in charge of doing this work one day. Let's say, not a water heater, but you got to install a motor. All right, they bought a new motor, a pump, you got to hook it up. And you have to know that you have to use now a two-pole. You can't use two singles. Now, again, can you do it? Sure, you can do it, but now you've violated the code. If anything happens to this, then you're liable for the work. Obviously, you're doing something that's incorrect as well. So it is especially important sometimes, not always for an industrial electrician to know code, but it is if you're going to do work like that. And one of the things that makes an industrial electrician a little bit more valuable is having a little bit of those skills that come with a construction electrician that sometimes industrial folks are not really learning because they're more, they're focused more on programming PLCs, worried about more motor control and diagrams and, understanding machinery operation versus knowing code. But knowing a little bit of code and bringing that into that world helps. All right, now this one to check. We're not going to worry so much about the neutrals. What we really want to check is between both of the phases. All right, so we want to check phase to phase here. All right, or we want to check hot to hot. Now, here's why I say that. If I take my meter here, right, and let's say instead, let's say I'm at the panel and this is the neutral bar inside the panel. All right, and I take my meter and go, all right, I'm going to go from the neutral to, let me erase this, one of the hots. And okay, I have 120 there. And then I check from the neutral to the other hot. And okay, I have 120 there. But that doesn't mean I have 240. It just means I have 120 twice. Now, it's unlikely that at the breaker you're going to have some kind of weird stuff that if you measure 120 here to neutral and 120 here to neutral, if you were to measure between them both, you're not going to read 240. It's very likely that you will 100% of the time read it. But it's good practice to not measure these like we measure these. Hot to ground and then hot to ground again. Again, taking the meter and going to some kind of ground. You can just go to metal or something like that. And then measuring here, reading 120 and then measuring there. We don't do it that way. The correct way to measure this is grab your meter. You set it to voltage, of course, and you put one here and you put the other one here. You measure phase to phase, hot to hot, and there you will read 240. One, you don't have to do this twice, ground to hot again. You have to do it twice. You just do it once. And two, that's it. You're 100% verified that you have 240 here. That's the important part. All right, so checking these, hot to hot. And now a 3-pole breaker. All right, these are for 3-pole motors. Any kind of 3-phase machinery will get a 3-pole breaker. Here again, now you're going to shut off 3. All right, just like this one disconnects 2 hot conductors. This is going to be 3 hot conductors disconnected. Simultaneously. There we go. I guess I'll. And now here's the difference. When we check this one, we're going to do 3 checks. Always on 3-phase. Practice checking all 3 phases to each other. Don't just check 2 of them. Don't just check like A to B and B to C, and then that's it. Walk away. No. Check A to B. Check B to C. And okay, yes, I've covered everybody, but let's check A to C as well. All right, this is a good thing to practice for 3-phase. Do the triple check. A, B, then B, C, and then A, C. Check all 3 of them and make sure all 3 give you the voltage you're looking for.
We found out the B is L1, right?
Yes. You also can see these as L1, L2, and L3.
And then A is L2.
No. A would be L1, B would be L2, and C would be L3. So L1 to L2, L2 to L3, and L1 to L3. We want to check all 3 of them to each other. The triple check. And again, this is not, like I said, this is not so important at the breaker to do it this way, but it's good practice, especially when you're at the load, when you're at a motor or something, when you're at outlet checking. Go ahead.
Can L1 be L3?
Say that one more time.
Can L1 be L3? Like, they don't like.
Yes, could I mix this up? Sure. Yeah, you can revert, you can do this. This is fine. This is okay. It doesn't really have to go in that order, and sometimes for motors, if you did the motors classes, you'll have done reversing,
Oh, yeah.
motor reversing, and when you do motor reversing, you switch up some phases. Reversing the phases will change the direction of the motor. Or usually what we do with that is you only change two of them. So you would just change the order, like it would be B, A, C.
Yeah.
You just flip these two. You can do any combination would work. You can do C, B, A, that would work as well.
Nice.
So any one of the three combos, and then you can leave A alone and then switch B and C. Either one is fine. And then you'd make the motor go opposite direction. Not forward or reverse, just opposite of whatever it was going. All right, so these are the three breakers, no other ones, no fourth. So a single pole, again, single pole, very small breaker. It's only for these lower amperages. And these are for individual circuits. If you need two phases, you don't use two singles. You use, same as you need three phases, you don't use three singles. I didn't mention that one for that one, but. And here you just check hot to hot, make sure you have your 240 or 208 or 480. And then three phase, you have to check it 3 times now. Don't just give up after you've checked 2 phases, check all 3. It's good practice to do it that way.
Those have to have 240, right?
These will have 3 phases, so this will be one of 3. It could be 240 in a high leg or a corner grounded. It could also be 240 in a any of the deltas could have 240, I should say. Any of the Ys, this could be 208, or this would be 480 as well.
Okay.
One of these 3, but not 120.
Okay.
All right, so these are our breakers. Now, the only thing I want to mention about a breaker, and I'll use the single pole to show this, and I'll use this individual one that I have here on the reset and test. All right, it's not in the order. I should have put this in order, but I guess I'll do that. Let me just move that over. There, that'll make more sense. So, if you know how to do this, great. If you don't know how to do this, you absolutely must know how to reset a breaker when you get out of this school. So here, I'll show everybody to make sure everyone knows how to reset a breaker. So first, what do I mean by reset a breaker? So, not on and off. On and off is on and off. That's not reset. So, off is always going to be towards the wire. And now, first of all, the breakers say it, but sometimes they're not so clear when they say it. Sometimes you got to look at it, maybe take a flashlight. So it doesn't really matter if you don't see it. It's towards the wire. Always towards the wire is off. And always towards the center of the panel, because that's what will be here, the center of the panel. Another breaker will be sitting across from it with, on in that direction. So this will always be on. So trip is when the breaker is dead center. All right, trip is when the breaker handle is in the center. And again, this goes for single phase, single pole, 2-pole, and 3-pole breakers. The handle will be dead center. All right. So when I say reset, it's off of a tripped breaker. Again, this is not on and off. On and off is just on and off. When the breaker trips is in the center. Now you need to know how to reset from there. And you don't just turn it on. When it's tripped and it's in the center, if you force it on, it's just going to drop back to the center. All right, to reset, you have to turn off completely. This actually does the reset. That is the reset. The off is the reset. And then you turn back on. That's how you reset a breaker after trip, right? This is reset after trip.
Oh.
Because when it resets, when you walk up to the breaker, when it's tripped again, the handle is going to be in the center position like that. It's even going to be wobbly. You're going to be able to move it. So you have to force it. You got to go all the way closed. Oh, sorry, all the way open, technically. Off. And then you go back on. And here, going back to yesterday, At that point yesterday is where I'm sitting there now and waiting. All right, now I'm sitting there waiting for, oops, not this one, for, not that one either, for this. I'm waiting for instant or take a little bit of time. All right, so I walk up to the breaker. It's in the trip position. How do I know? Because the breaker's in the center. The handle's in the center. I turn it all the way off now. I turn it all the way on and trips instantly. Short circuit ground fault. Takes a little while to trip. Then I'm leaning more overload or bad breaker. All right, but it comes off of knowing how to reset. All right, and again, the reset is after the breaker has tripped. All right, so again, breaker trips in the center, handle all the way out, and then back forward. And that's it to breakers. There's no, we're going to do fuses next, but there's no more single pole, 2-pole, 3-pole breakers. When it trips, handle's going to be in the center. To reset, you got to turn it all the way off and then back on. All right, other than that, understanding the amperage, but that's not a maintenance person's job. All right, setting the amperage and deciding wire sizes, that is the construction people. When you open up a panel, hopefully everything was done correctly. And if it's not, we'll find out. All right, let's move on to fuses. All right, move on to fuses. Now, there's a lot of size fuses. All right, there's a lot of size fuses. There's little ones, there's wide ones, very tall, thin fuses. So fuses are going to have a class. All right, fuses come in a class. This is a, let me go into, see if I can find a fuse class chart. There we go. I'll be able to find a chart here. I don't want to complicate it too much that you have to memorize these, but let me go over to a fuse chart. No, that's not a great image of it. 1 second. There's, let's see, a simple version here. There isn't a simple one. The reason why there's not just a simple one that I can click on is because there's a lot of them. So I'll show a couple. All right, let me just go over to what I'm looking at. So they come in class, like I said. So we have class of fuses. Class T, class H. Yes, that word is, but it's used in the fuse world. All right. We have, going back to where I was at here. We have other types. Class RK1, RK5, Class L. You do not have to memorize the classes of the fuses. There's a lot of them. Like I said, I tried to pick a page that just gave me one. It's very difficult for me to find a single page, you know, an easy to read fuse class breakdown, all right? So there's a lot of different styles of fuses, but there technically is only 2 types. Styles and class, there's many. Again, the H, the L, the K, the Y, these are just big fuse, wide fuse, little wide, thin one, has a, you know, this format. Okay, so they look differently, but there's only 2 types. All right, it's only 2. Technically, there's a third one, but I'll give the third one an honorable mention in a second. There's only 2 types. The 2 types are glass fuse. All right, the glass fuse. These are going to be for low current systems. All right, these are for low current systems. And they're usually somewhere in the 1 amp to 3 amp world. And mainly, not always, but mainly used for not motor control specific, but controls. Motor control, lighting control, automotive control. All right, if you open up your car's electrical little box, you will find this tile fuse there. This is a glass fuse, all right? The thing with a glass fuse is you can see through it. You can see the element. That's what that little thing there is called. It's called an element. You don't have to write that, but you do want to grab these as notes. Now, the idea of the glass fuse is twofold. Actually, I wanted to apply a voltage here as well. These are going to come in 125 to 250 volt rated. All right, they don't go past that voltage rating because they're used for control circuits, and usually they're used for very low voltage control circuits, meaning 12 volts would be fine. That fuse right there is holding for 12 volts. For my online students that did their labs, you guys will remember your motor control labs came with these little glass fuses. Online as or in person as well. I don't know if Phil showed you these little fuses and when you guys were troubleshooting, but they're low amperage fuses because control circuits have very low amperage in them. So the idea of this fuse is simple. You should be able to look at whether or not it's damaged, although I will say don't trust that. Now the other type of fuse, and this is the one that has all the different classes, class F, class J. I think the code book has the letters. I'm not sure. You definitely could find the letter system somewhere. But these are called cartridge. And that's it. These are only two types. A bunch of models here, a bunch of different class here, but they're all cartridge fuses. All right, this is a cartridge fuse. All right, now this is going to be for high current. I'll explain the design. There's a design difference in these. There's a reason why they're built this way. Sorry, I meant to write that neatly. High current. This will go from the smallest amperage we have to the largest amperage we have. So smallest amperage we have is after 3 comes 5. So these will generally be in 5 amp all the way down up to 6,000. That's the biggest fuse that they make is 6,000 amps. All right, and these are used for anything from motors, main distribution systems, but not so much. I would say these are used more so for motors or for equipment as well. All right, big amperage fuses. All right, and they use them for main distribution as well. But a lot of times main distributions would rather have a breaker than a fuse. But you can have fuses or breakers. It doesn't matter. Homes generally have breakers, although there is another fuse. The only one I'm not mentioning is because it's for residential. It's called an Edison base fuse. You may have seen the little, all right, the little circle ones like here. All right, you can see the name down here, Edison. All right, down there it says Edison. Eaton is just a company, but it's a Bussmann. Because that little thread right there, the screwing in on that fuse is the same size as a standard light bulb, and a standard light bulb's thread is called an Edison base. All right, it's called an Edison base because Thomas Edison, you know, the light bulb and all that fun history. Now this fuse, I mean, I don't think you're going to run into this in an industrial or commercial setting unless maybe it's an old building or something like that. But there is a color coordination to these. There we go. I'll pick this one. There was a better one that used to come up. Yeah, there's a color coordination to them. I'm not sure if you can see them that well. See if I can pull that up. Nah, it's not gonna let me show the image as well. But the colors used to tells you the amperage. You can see a little bit more up close in that orange one. It's 20 amp. All right, if I pulled up the blue one, all right, there's the blue one. It's 15. Orange is 20. I think red was 30. No, green was the 31. These are a little bit out of, they predate me. I think blue was 25. I don't remember. But these are the old ones in homes. That's the other type of fuse out there. But you don't need to know that one as well. Or as much. All right. Now, these fuses of the cartridge fuses here, I meant to say, of the cartridge fuses, there are 2 types of cartridge fuses. And so I have the notes here. That's where we were heading over. All right. The 2 types of fuses are quick response fuse or a slow response fuse. You have a fuse that's going to delay blowing or tripping, however you want to say that, after the amperage has exceeded. In other words, all right, I have a fuse here. All right, let's say it's a 40 amp fuse, and I have it connected to a load. Depending on which fuse you have, if this load starts to climb an amperage a little bit, it's a motor, it's starting to seize up a little bit, and we're starting to climb an amperage, and it goes to 42 amps. One of these fuses is going to respond in 1 to 3 seconds, and one of these fuses is going to let that go for a little bit and not respond for about 8 to 10 seconds. All right, some books tell you 8 seconds, some books tell you 10 seconds. Now, the reason is for the use. Depends on the use. When a motor starts, a motor generates a lot of energy right up front when the motor starts. So, you don't want a fuse that when the motor starts and you get this jump in amperage just for a second, and the motor climbs up in amperage to like, 2, 3, 4 times its normal amperage, but it only does that for about a second, just in the motor startup. If you have a non-time delay fuse, now we'll look at the two names. There is a non-time delay fuse. That is not a good fuse to use on a motor because every time the motor starts, you're going to lose this fuse. So you want to use a slow reacting fuse or a dual element time delay. More so, remember the time delay part of that fuse. So non-time delay fuses, they're good for your main distribution panels. All right, if I have a main distribution fuse that's 100 amps and I'm at 100 amps or 101 amps, I want that fuse to go now because it's a main distribution panel versus a motor just starting, just normal motor startup. We don't want a fuse to blow every time a motor normally starts up. So they're used differently. All right, a few more things and then we'll wrap up. So fuses, where do they live? Well, fuses live in fuse disconnects. All right, this is where they live. They don't live in panels. All right, fuses don't, there's no fuse panel. Now, except for the Edison one, but like I said, that's only in old residential areas. If you're in an industrial commercial building and you're, looking at a 3-phase motor or a air conditioning system and it has fuses, it's going to be in a disconnect. All right, it's a disconnect. And specifically, it's a fused disconnect. All right, now the things that I want you to know about a disconnect are the top or the line side. Always hot. Very good. Always hot. All right, the bottom is only hot, or this is what we call the load side, is hot when on. And then position. On is up always. And as you can see right now, it's in the off position. So the reason why I want you to know that is for visual. Right? You can do a look at the disconnect and just see it. Oh, it's off, or oh, it's on. And this should be something that you've memorized because switches work the same way. You lower a switch, it's off. Go up with the switch, it's on. The reason why I want you to know top line, hot always. Oops, I didn't write always. You said it and I just let it go. Bottom hot only when hot is because I have seen this. I've seen people land the load on the top. The part that's going to the motor, they've landed it on the top, and the power coming in, they've landed it on the bottom. I've seen people make that huge mistake, which is dangerous now. Because now when you shut it off, it's in the off position, but the power is still on down here. And this is not built to be wired up that way. You can see this red protective shield is on the top part, protecting the hot wires that are always hot. Oh, 1 second. I got a little cockroach that is joining me. I'll get him in a second. Now, every time you see these, are they fuse disconnects? No. Some of these have no fuses. They look the same, but they're not. They're called safety switches or service switches. I've known them more as service switches. Maybe it's a Florida thing or a East Coast thing. Say if you go to order these online, like at Home Depot or any supply house, safety switch is what you have to write in. And these that's the note here I want to put. No fuse in a safety switch. No fuses. All right, these are only for, that's why I call it a service switch. This is only to be able to provide service. This is just to turn off and lock out. All right, so you're able to lock in. You can see a little bit better here where there's a little hole there that I can place my lock in the off position. All right, same thing here for this one. So this is what I'm not going to go to the article, but it's in Article 430. I used to have it memorized, like 430.18 or something like that, or .20. It says in that article that every motor, 1 horsepower or above, every motor must have a means of shutting off the power located within 50 feet of the motor, and I have to be able to see the switch, the off mechanism. So usually it's one of these, either this one or this one, doesn't matter which one, and usually it's nearby. We never put it 50 feet away from the motor, unless there's some kind of reason to do it, you know, because there's things around it or something like that. But usually you have this disconnect and you're fairly close to the motor. Now, does it have to have fuses? No, that's not what the code says. The code just says you have to have a means of turning off the power visible within the motor. In other words, you know, because if the technician has shut it off, they want to be able to see somebody come over and turn it on, get their hands all chopped up and stuff. So this is where the safety switch comes in, because it's more expensive to buy one that's going to house fuses, plus you then got to buy fuses, versus I don't need that. I just need the switch to turn on and off to provide safety or service ability, so I don't have to put fuses in them. All right, and again, since we're talking power distribution, all right, this is only an on-off switch. If I'm looking for power out on my motor, or if I'm looking to see if I've lost fuses or something, then I am going to go to a fuse disconnect. So when you're out in the field, you open one of these up. If you see fuses, okay, you know what you're dealing with. And if you don't see fuses, okay, you know what you're dealing with. All right, we're getting down a little bit late. I do want to show you guys how to test a fuse, but this is going to take me a little bit of time, and there might be some follow-up questions. So we're going to pick this up tomorrow.